using remote sensing, crowdsourced data, and numerical models. So, so everybody knows about the urban heat island effect, which is the phenomenon of higher temperatures in cities compared to the surroundings. And it is probably the most studied topic in urban climatology. The urban heat island effect also tends to vary with background climate. Generally, in humid regions, you have higher urban heat island versus in arid regions where you can have either a very small urban heat island or sometimes even an urban cool island. There's both observational and modeling evidence of this, and this is driven by differences in cooling processes and the biophysical properties of the background climate. Urban areas also have a large amount of heterogeneity, which leads to large differences in temperature across different parts of the city. And due to population and urban structure covariance, this can actually cause disparities in urban heat exposure, which has been seen quite a bit in US cities. Now, one of the things about all of these large scale multi city analysis is that they're either done using observations or models because we don't have a lot of air temperature measurements in cities. Sorry, either satellites or models. So that means that for satellites, you're primarily measuring surface temperature. But surface temperature is not air temperature, and it has been an issue in the urban climate literature that a lot of results from surface temperature are often kind of discussed in terms of heat risk and also in terms of policies, which is difficult to justify because these are two different variables. And this is just not true for observations. Even models sometimes use surface temperature because just because of the strong coupling between surface temperature and the energy budget, it's easy to diagnose different changes in the surface temperature. So, in a series of studies, we have been looking at how the coupling between different measures of heat vary across scales in urban areas. And in the first study, we looked at citizen weather stations over Europe. So, we had over 50,000 citizen weather stations from this company called Netatmo during the July 2019 heat wave period. We examined the urban warming and drying effect across over 600 urban clusters. And we also looked at within city variability by creating what we call the decile regions of surface temperature. So we start from the first decile, which is the coolest part of the city, to the 10th decile or the warmest part of the city, as seen by satellites. So first, we just look at the surface urban heat island versus the air temperature or canopy urban heat island. So here we see the diurnal variability, and you can see that the diurnality is different. The surface temperature, surface urban heat island is higher during daytime, while the canopy urban heat island is higher during nighttime. This is well known and is consistent with a lot of case studies over multiple decades. Here we just had a very large data set to show this signal being consistent across cities. Similarly, if we plot the what is kind of equivalent to the surface urban heat island against something equivalent to the urban heat stress island, here heat stress is defined by heat index, which gives a combined impact of temperature and humidity on overall thermal comfort. We also use several other moist heat stress indices. I'm not showing all of the results here. But basically, the urban rural difference in daytime heat index is much lower than the urban rural difference in surface temperature. And in only half of the clusters, we actually see any positive daytime heat index island for this period over years. Similarly, when we look at the intra-urban variability, you can see that, of course, air temperature increases in the surface temperature decile regions, but the magnitude of increase is much less than what you see for surface temperature. Similarly, for relative humidity, you actually have the opposite effect. Warmest parts of the city are usually the driest, which means that there is this compensating effect due to the increasing temperature and decreasing humidity, which ultimately leads to less variability in the heat index than for surface temperature. Quite a bit less. Like these transparent parts mean that there is no statistically significant difference from the background reference values. Similarly, when we look at the variability of the urban, heat signal across background climate, which is done with precipitation rate as the proxy, which is very common in the literature, we see an increase in the surface urban heat island in wetter climate compared to drier climate. This is also kind of seen for air temperature, or canopy urban heat island, but again, the magnitude of change is much lower. For the urban dry island, you see the opposite effect in that the urban dry island effect is the strongest in humid climate, and is almost zero in arid climate. So again, you have this kind of thermodynamic moisture feedback, which moderates the relationship of the heat index island against background climate. And this is important because a lot of large scale studies have talked about how policies should be catered to background climate, but then using surface temperature heat islands. And this shows that that may not be reasonable. Finally, we look at the, I don't know what happened at the top here, but when we want to know if the variability of the surface urban heat island across cities is a good proxy for the variability of the canopy urban heat island. And you do see a positive association. It is very weak, and the slope is around zero point 0.2, which means the surface urban heat island is around 5 times more, not variable, has a 5 times higher range than the canopy urban heat island. The dry island has the opposite effect, like the counter correlation, where cities which have a higher surface urban heat island tend to also have a higher urban dry island. And then with heat index island, you kind of get that moderating influence of the drying and the warming, and you have like a slope of 0.17. So overall, this tells us that the urban-rural difference in surface temperature is a poor quantitative proxy for the corresponding difference in heat index. And this is partly due to the compensating humidity feedback. So we haven't still looked at the disparity question because that's a big issue, particularly in US cities. And citizen weather stations are not the best way to do it, just because there's a lot of sampling bias in citizen weather stations. Like, obviously, it's not the poor urban residents who are buying private weather stations and putting it in their backyards. So in this case, we had to use models. So we ran a single layer urban canopy model at 1 kilometer resolution over the continental US. And then we aggregated the values for around 5 years into census tracts for over 480 urbanized areas in the US. And then we calculated heat indices like humidex and the heat index. So on I won't say positive note, but we do see pervasive disparities in moist heat stress across US cities. And interestingly, the magnitude of the disparity is also strongly associated with the degree of racial segregation, which is seen in this quadrant plot on the right. However, that's only true for the magnitude of disparity. When you look at for the direction of the disparity. When you look at the magnitude of the disparity, there you can see that for land surface temperature, and the magnitude here is given by the slopes of linear models against, say, income or fraction of white population or black population. But what we generally see here is that its LST variability against income is more than double that for air temperature, humidex, and heat index. Another thing to note here is that I have put LST and TSK separately. Like, TSK is the simulated skin temperature, and the reason for that is satellites basically give you a directional measure of skin temperature, which is not usually equivalent to what the urban canopy models are simulating, just because of the structural assumptions in many of these models. And also, like, when we are doing this comparison, it's best to just focus on the modeled variables because they're constrained by those same structures versus what the LST are looking at, satellites are looking at. So the previous analysis was using uncoupled simulations. We did bias correct it against observations, but there are a lot of potential issues with using uncoupled simulations. So in a different study, we actually ran ensembles of coupled simulations using the WRF-BEM model over the Great Lakes region, and then tried to understand the disparity of these different metrics over community areas in Chicago. We also considered multiple configurations, including different boundary layer schemes, one-way versus two-way nesting, and different complexities of urban representation in the model. And as you can see from these plots, these are for like the different configuration. For daytime, there is very strong consistency. Skin temperature shows strong disparities when you look at like the slopes against income per capita income. Air temperature shows less variability, and then finally a wet bulb globe temperature, which includes not just temperature and humidity impacts, but also wind and solar radiation. However, for nighttime, there are a lot more inconsistencies, and part of that has to do with how the different models incorporate anthropogenic heat flux and how they interact with the boundary layer scheme. So we are still trying to figure out why there is this much inconsistency at nighttime. So kind of the take-home message here is that any urban signal on surface temperature is probably going to significantly overestimate the signal on air temperature and heat index. So we should be very cautious about using these quantitative estimates from either modeled or measured surface temperature when discussing public health. Another thing to note here is that the strength of the humidity feedback depends on the heat stress metric or proxy used. Heat index is most sensitive to temperature, so this gives you like the most conservative case of, or like the least humidity feedback rather. We also use wet bulb temperature and many other metrics. Wet bulb temperature being the one used most commonly in the earth science community as a proxy for heat stress. And we found that in that case, the compensation for warming and drying is almost like complete. So tomorrow I will actually be touching upon a different issue related to this, like using LST to get vegetation cooling signals. I didn't have time to cover it here. Thank you. Here are a bunch of references for the work I discussed. And I am also starting a project on improving urban representation in an Earth system model in a globally consistent way, and looking for a couple of postdocs. So if you're interested, please reach out to me. Thank you.
Thanks, TC. Questions?
I'm very interested in your the urban camping model you run covered over all the USA. So
Yep.
you said it's a 1 kilometer resolution. Right?
Yep.
What's your forcing data for?
That is the HRLDS forcing, which has been downscaled to 1 kilometer.
Okay.
So that data set.
My talk is related to you. So we downscale the forcing data, or we just run at the forcing data?
No, we downscale it.
That's a problem. Yeah.
And that there is a data paper also coming out soon. So we only use 5 years of data here, but it has 30 years of data at daily resolution.
Thank you.
More questions? So I noticed that you had that plot where you had the urban heat island surface temperature and air temperature, and they weren't that well correlated. You said it was due to the relative humidity.
I think relative humidity is a much smaller, much smaller impact than just the coupling between air temperature and surface temperature itself.
Okay. So the reason that they're not that well correlated is what?
I mean, this is pretty well known conceptually. Like if you have impervious surfaces, you don't have a lot of evapotranspiration. So all of the dissipation is happening through sensible heat. So if you're moving from more vegetated surfaces to impervious surfaces, your sensible heat flux goes up, assuming everything else is constant, and the gradient of temperature or the temperature gradient between surface and air also goes up. So that's the decoupling that we see. And this is also very well known when you look at like arid climate versus forests. That in arid climate you have a lot more difference in surface versus air temperature versus in forested or grasslands where you have like closer values between the two. So this is true in natural environments. In urban environments, you have that variability in a much smaller region, which is causing this decoupling on the spatial scale.
Thank you. I think we have just about time for a quick question as well.
I think you mentioned that in more impervious areas, the higher built-up areas, the humidity kind of is less that you've noticed. Can you explain the processes that actually cause this?
I mean, the first one is, of course, if you have impervious surfaces, you have less humidity as a whole because there's less water being evaporated. But the other is that temperature itself controls relative humidity, right? So there's like, even if you kept the specific humidity the same over the urban area, warmer areas would have less relative humidity.
That makes sense. Thank you.
Thanks again, TC. So next up.